Hey guys, welcome to our live session. My name is Matt Shell. Hopefully you guys can hear me okay. How do I sound out there in internet land? We're going to be starting in about 1 minute with our live session on machine learning agents, which should be really cool. Feel free to post your comments in the chat. We're going to have some members of the team who are working on machine learning agents joining us. Which should be a great opportunity to ask questions of them. I'm sure you have some. This is a new topic for me, so I'm looking forward to learning more about it as well. I understand some of the basics, and so we'll be able to jump in with some answers, but I'll be relying on I'll be lying when I give you answers. I will be relying on Arthur and Hunter for the nitty-gritty technical details in terms of answers. I'm always lying when I give you answers. So that's the fact of the matter. But yeah, it should be a lot of fun. We are going to, we're going to go live right now because it's 8 o'clock. Okay. Hi, and welcome to our stream on machine learning agents. So this is a stream which is going to be presented by Arthur Juliani and Hunter Henry, who are members of the team working on machine learning agents at Unity. So this is a super, super interesting topic for a lot of us. For those of us who have kind of engaged with, what we call AI in the video game sense, things like state machines and behavior trees and stuff like that, this is a very different approach to creating behavior for video game agents based on something which is much more like kind of real life learning. So super, super interesting, quite different from some of the stuff that we may have done before if you followed some of our previous programming streams around some of these topics. So I'm really, really excited to bring this to you. And so without further ado, I give you Arthur and Hunter, who are also here in the chat. So feel free to post questions while the video is running, and I will also be there in the chat with you to answer some questions as well. So let's take it away.
Hi, thanks for joining us. I'm Arthur.
And I'm Hunter.
And we're both from the Unity ML-Agents team.
Today we're going to walk through an example of the ML-Agents toolkit. We'll be showing you how the code works, how to set it up in the editor, and how to train an ML agent. So let's get going.
Before diving into the editor and the code itself, I want to spend some time talking about what ML-Agents is, what machine learning is, and what it means to use machine learning in games. Now, first, just a brief overview for those unfamiliar with machine learning. Machine learning is essentially any way to, instead of coding, hard coding behaviors or hard coding computer interactions, we allow the machine to learn from data how to act. So this approach to learning from data is used in a wide number of applications out in the world. One of the most successful in recent years has been image understanding. So we can think of a machine learning model, pictured here, as a way to take an image and map it to something else in a learned way. So in this case, we're mapping the image of a sunflower to class labels about what that image is of. In this case, we see that the image of the sunflower outputs at the right a high probability of being a flower, and we'd consider this a successfully trained model. Now, we can take this same approach to learning from large amounts of data and apply it to games.
Okay, cool. So we had a quick question in the chat, people asking, is this something that we should be following along with? The answer is no. This is more of a kind of an intro overview. Since this is quite a new topic for a lot of us, we're going to have a kind of a conceptual overview as Arthur started to give there, and then we will get into some code and some implementation in Unity, but it's not going to be kind of stepwise, do this kind of stuff. All right, I'm not going to talk too much. Let's keep going.
We can take machine learning and apply it to games in a number of interesting ways. Most of these come about from realizing that we can take this same mapping that we used in computer vision and apply it to actual controls of an agent in a game. So we can take the input, which is now, instead of being a picture, it is perhaps the game screen or some state that the agent has access to. And our outputs, instead of being class labels about what that picture is of, can be what's the best move to take or button to press on a controller, given our current state of the game. With this in mind, there are a lot of different ways in which we can attempt to teach agents to learn the optimal mapping or desired mapping from observations to actions. The two most prominent methods, and the two methods that we provide algorithms for with ML-Agents, are reinforcement learning and imitation learning. Let's start with reinforcement learning. In reinforcement learning, the primary learning signal is what we call a reward. This reward is a scalar value that can be provided to the agent at any time during the simulation. And you, as the developer or creator of the environment, get to choose what that reward is and when it's provided. We can think of reinforcement learning as being very similar to the way in which people train animals, or pets, for example. Say you want to have a dog learn to do a trick like roll over. If it rolls over successfully, you can give it a treat. Now, in the dog's brain, the dog will learn to associate the treat that you just gave it and the situation it was in and the action that it took, which was to successfully roll over. It's now the case that the dog is going to be more likely to do this trick in the future because it's expecting the reward. The same exact principles apply to agents in virtual worlds and virtual actions. Here, by providing agents with positive rewards and negative rewards, we can encourage and discourage the behavior that they have, slowly shaping their behavior until it exhibits the desired properties we want, like being able to solve some task. In addition to reinforcement learning, there's imitation learning. Unlike reinforcement learning, where a reward signal has to be defined for interesting behavior to be learned, imitation learning simply requires a set of demonstrations. These demonstrations are simply observation-action pairs, which can be recorded directly from a keyboard or gamepad, and these observations can be provided by a player or a developer actually playing the game. This is an appealing option in scenarios where the reward function is difficult to define by hand, and it's simpler to just show the agent what playing or acting correctly looks like.
Okay, cool. So some kind of top-level definitions. The imitation learning is a newer piece that's added in ML-Agents 0.3. If you weren't aware, this is a new release that the team has just brought out that you should definitely check out if you haven't already. And so let's just continue right along.
With these concepts in mind, it's time to dive into the actual ML-Agents workflow. This workflow can be broken into 3 high-level steps: creating our environment, training the brains in that environment, and then embedding those trained brains back into the Unity scene. We'll walk through each of these in order. To start with, we want to create our environment. In a little bit, we'll show you exactly what that looks like in the editor and in the code, but right now I want to walk through what that conceptually looks like at the level of ML-Agents. In ML-Agents, we introduce 3 new concepts: the agent, the brain, and the academy. At the lowest level, the academy is what allows everything to work together, and it's what allows Unity to communicate with outside training frameworks like TensorFlow using our Python API. At one level up from that, we have the brain. The brains are what actually make decisions, and these can be thought of as our neural networks. Now, with these brains, we need things to actually take these decisions and act on them in the world, and these are our agents. Each agent observes the world at any given step of the simulation and uses that observation via the brain to take actions in the world. What you can see here is a relatively simple diagram where we have 2 agents being controlled by a single brain. We can make this more complex, as seen in this diagram here, where we now have 4 different kinds of brains, each controlling multiple different agents. You can imagine an African Sahara where you have different kinds of animals, for example, elephants, lions, and zebras. Each of these kinds of animals would correspond to a different brain, which is a different way of taking actions, the way in which an elephant might, a lion might, or a zebra might. Then we have the actual agents themselves, which correspond to the actually living animals, of which there may be many. Now that we've shown you what this looks like at the conceptual level, let's jump into the Unity editor itself and see what it looks like there.
Okay, cool. So getting an overview of some concept. We had a couple of people in the chat asking about just the interface on Connect. The way that the video is laid out on the page is a known issue. It's something we'd like to improve. If you want to, you can pop out the YouTube embed, because we're streaming via YouTube, just by clicking on, mousing over the window and then clicking on YouTube, the YouTube icon. That'll pop it out for you so you can have it as a floating window. But yeah, right now the way that the screen real estate is used is not perfect. So there's a couple questions in here. Folks asking about bringing in things like real world data or data from beta testers, that kind of stuff. I would punt those back to Hunter, who's there in the chat. But my understanding of this, and kind of as we saw in the overview, is that the ideal use case here is about training agents about the simulated world in Unity, right? It's not so much about taking in outside data. It's more about, let's simulate a world, let's teach the agents to understand it and act within it. Obviously, you could create, somebody was mentioning tennis, right? You could create a tennis simulation, maybe that mirrored some real world conditions, but I don't know if it's going to be the perfect case for using real world input data. Yeah, as Hunter says, definitely maybe, but it would depend greatly on the implementation details. So I think that the kind of my understanding of this anyway is that the best use for this is to teach agents to reason about the virtual world, right? As opposed to, the real world, for example. Obviously, you could, make some interesting conclusions, but it's really about teaching them to think inside of a simulated environment. Okay, let's continue.
All right, now that we've gone over some of the high-level concepts, let's jump into the Unity editor and have a look. You can get the ML-Agents project by going to Unity Technologies/ML-Agents. After you've downloaded it and imported it into Unity, you'll see a folder structure. Inside of the ML-Agents folder, you'll notice that there's a folder that says examples. These are going to be where the different example environments live. Today we're going to be talking about the push block environment. So let's find push block. You'll notice a folder that says scenes. Go ahead and open up the push block scene. I already have this environment open, and it should look like this once you have everything open. Once you have the project open, you'll notice there's a game object called Academy. On the Academy game object, there is a script called Push Block Academy. This is the Academy script for the scene. The Academy orchestrates the decision-making processes for the brains that are in the scene, and in addition to that, it also has some environment-wide parameters and variables that's used by different things in the scene. Let's walk through some of the settings. The first setting is max steps. This is how many fixed updates are going to happen before the Academy resets itself. When an Academy resets, it essentially resets everything in the scene back to the way it was whenever it started. If it's a 0, that means that there is an unlimited number of steps and it's not going to reset itself. Next, we have training configuration. This is the configuration that's going to be used whenever an agent is actually training. We can set the resolution, the quality level, timescale, and target frame rate. Out of all these settings, timescale is going to be the most important. That controls the speed at which the simulation is going to happen whenever an agent is training. You want to make sure that you don't set this too high, or it could just bog down your system and result in a slow and poor simulation. Next, we have inference configuration. Similar to the training configuration, you can set the resolution, quality level, timescale, and target frame rate. Reset parameters we're not going to get into just yet. We're not using any reset parameters for this environment, but if we were, they would be configured here. The next settings that we have are custom settings that we're using specifically for this environment. So agent run speed, this is going to be the speed at which the agents in the scene can run. We have agent rotation speed, which is the speed at which they can rotate. Spawn area margin multiplier, it's a terrible name for a variable. However, what it means, it is the percentage of the area that an agent can spawn. So, for example, 0.5 means that roughly 50% of the area here, an agent can spawn. We have a goal scored material, we have a fail material. This is just a green and a red material. Whenever an agent scores or fails, the ground will light up with either a green or red. And finally, we have a gravity multiplier. This just increases gravity on a wake so that things look less floaty.
Okay, cool. So some folks asking about, Jason was asking in the chat about the fact that the environment setup for ML agents requires a bunch of external libraries and so on. I also had that experience setting up on Windows, that there was a bit of doing that had to get done to get it working. On Mac, apparently, it's quite a bit easier because a lot of the libraries, the Python libraries, are already there. But yeah, if you're not a Python person already, it can take a little setup. We do intend to make it more user-friendly and more tightly integrated with the kind of Unity, the world of Unity. But the goal right now is, because tools like TensorFlow and some of the other popular machine learning libraries that are already out there already use Python, we want to be able to leverage those and be compatible with them, which is why we're using Python here. And obviously, this is the 0.3 release, right? So this is still a very, very early stage of the product, and it's not kind of like in a full product release state. But of course, we want to get it to you early so that you guys can start playing with it and giving us feedback about where we should go with it. Okay, let me just look at any other questions. iBite asks if imitation-based training could be done in VR to develop data that could be applied to the same scenario in the real world. For example, training a robot to do something. As Hunter says, that would be neato. I agree. That would definitely be neato. Not quite yet. The reason being, as you'll see later on when you see the actual training run, at least for the reinforcement learning, it's not running in real time. I mean, I guess maybe, yeah, maybe, well, this is for imitation, the question's about imitation learning. So maybe, but not yet. I was about to go off on a tangent and say something wrong. I caught myself. Ha ha. Okay, let's see. Yes, there will be, this will be uploaded to YouTube very shortly. So make sure you subscribe to our YouTube channel and you'll get a notification when it comes out. Not the quick Q&A part, but the actual videos. Let's take a look. Okay. All right. We seem to be up to date on questions. Okay, so let's continue with our next segment.
With the Academy and the brain set up how we'd like them, it's time to turn our attention to perhaps the most important aspect of the training process, the agent itself. We can find our agent game object within the area game object as a child. When we look at it, we find that it has attached a push agent basic component, and this component inherits from the agent class. By inheriting from the agent class, it gets a lot of properties that are specific to actually training the agent. The first one is the fact that we can now link a brain. By linking a brain, this means that we want to use that brain to make decisions for this agent. We can do this programmatically, but we can also link the brain by simply dragging and dropping the brain game object into the brain area right here. Next, we see that we have the ability to add and remove cameras. If we were interested in using cameras as observations for our agent, adding a camera is as simple as pressing Add Camera and dragging the camera over. We won't use a camera though, so I'll remove it here. Next is max steps. Max steps, like in the Academy, corresponds to how many fixed updates we want to perform before we terminate this specific training episode. In this case, for this agent, it's going to be 5,000 steps. Next is reset on done. Reset on done corresponds to whether or not we'd like the agent to, once it's set to done, reset. Now, how is an agent set to done and why? Agents are set to done by calling either done from within the C# code or by having the agent reach its max steps. And we set agents to done to restart the training process for that agent in that episode and move on to a new episode. Next, we have on-demand decisions. Here we have it disabled, but if you checked on-demand decision, instead of having agents take decisions at a fixed frequency, we can have them pick when they need decisions. This is great for turn-based games, strategy games, and board games, where agents might need to take turns and wait before making a decision. Lastly, there's the decision frequency, and this corresponds to how infrequently an agent should be making decisions. If we were to set this to 1, that would mean that every step of the engine we'd want our agent to make a decision. We set it here to 5 because making decisions that frequently isn't very helpful. Between any 2 steps of the engine, not a lot has changed. It's typically the case that decision frequency for most environments is between 3 and 10. With all of these components set up and our game objects set in the scene the way we'd like, it's time to now turn our attention to the code itself and look at how we've implemented the ML-Agents specific functions.
Okay, so before we get into the code, Vladimir, who's part of the team at Unity, posted the project about, I think it's called, is this Vision Zero, about autonomous cars and designing safer cities through simulations, which is a super, super interesting post by Jose, who works for Unity as well. Really, really interesting about computer vision models and autonomous vehicles, which I just find to be just like a super fascinating subject. So in this case, right, we're definitely interfacing with the real world because we're looking at a camera feed of the real world. Super, super cool. And in that case, right, we're trying to build a virtual environment that looks enough like the real world that an autonomous car could train by looking at the visual representation of it. Okay, let's see. Okay, not a ton of new questions. Yeah, Nelson points out that initial development on self-driving car technology was performed in video games like Grand Theft Auto, which makes sense, right? Especially if it kind of looks enough like a road. All right, I'm just back reading. Some folks asking for examples of machine learning. Okay, I think we're good in terms of questions. Feel free to put questions in the chat, and then we can answer them in the next Q&A. Let's continue.
With the Academy taken care of, we can then move on to looking at.
All right, so let's have a look at the code. We'll start with push agent basic. This is our agent script. We can see that it inherits from the agent parent class, which is going to give us access to a couple of different useful functions and methods that we're going to be using. Now, remember that the overall goal point to using this agent script is we need a way to tell the agent how it's able to take observations of the world, how it's able to take actions in the world, and also to define the reward function that the agent is using to define its behavior. We can initialize an agent, which is used to set up the agent. We're going to be setting up references to different items that the agent's going to need. For collecting observations, remember this is how the agent is going to learn about the world. In this example, we want our agent to learn about the world using a whole lot of raycasts. So this function here, we can see that we're defining a raycast distance, raycast angles, and what we're going to do is in the scene, we're going to tag different objects with different strings. So the block is going to be tagged with block. The goal is going to be tagged with goal. and the surrounding walls are going to be tagged with wall. This add vector observation method here is a method that we have access to because we are inheriting from the agent class. And the point of using this is we can feed it observations about the environment, and it's going to add it to the observation list that goes off to the brain. We'll walk through this script here in just a little bit, but for now, just realize that this method here is adding the results from our raycast to our observation array. The other important thing about this script is our agent actions. So after we have learned about the world using raycasts, we want the agents to be able to take different actions. You can see that in this function we have a move agent method here. Let's have a look at that. So in move agent, we're passing it the float array for the actions that we can take. Now, because this is a discrete action space, it's only going to return one value. So you can see right here, our action is going to be the first item in the array, and we need to cast it as an int. That int we're going to use in a switch statement. If it returns a 0, then it's going to go forward. If it returns a 1, it's going to go back, etc., etc. So our available actions that we can take: move forward, move back, move left, move right, and then we're also including rotation in this action set here. After it returns that, we can rotate the agent and we can add our force so that the agent moves. Okay, so whenever an agent scores a goal, we need to mark it as done. And whenever we mark an agent as done, again, remember in the editor, we are marking it as reset on done on the agent script. And so whenever an agent resets, it's going to reset the agent's position, its velocity, its angular velocity, essentially resetting everything back to the starting state, except for the fact that it's going to put the agent in a randomized location. Okay, so how does an agent know when it gets a reward or when it gets a penalty? Because this environment is pretty straightforward and simple, there's really only one way for an agent to get a reward. Whenever the orange block touches the goal, the agent will get a reward. If you notice on the orange block, there's a script called goal detect. And all this script is doing, it's using onCollisionInner to detect when the orange block touches a game object that's tagged as goal. When that happens, this function is called I scored a goal on the agent script. Let's have a quick look at that. Okay, so here we go. So when I scored a goal is called, the agent gets a reward of 5. The agent is marked as done. We successfully scored a goal. We need to reset, respawn, and try again. And finally, the ground material is swapped to indicate that we scored a goal for half of a second. Okay, let's talk a little bit more about the reward function. In this environment, the agent comes to realize that the only positive reward is given whenever the orange cube touches the goal. There is a negative reward that's given to the agent every single step based on how long it takes to complete its task. The point of doing this is to encourage an agent to hurry up and complete the task as soon as possible.
Hunter mentioned earlier that we're using ray perception for our agent's observations. I want to talk a little bit about how we do that. We do it using this ray perception component, which we attach to our agent. Looking at it in particular, we see that there is this perceive function, and this is the function we call twice within collect observations on our agent to actually collect all the observations necessary. The way this function works is it takes in a distance, which describes how far away the rays should be shot, a float array of ray angles, which correspond to the angles that the array should be at relative to the agent itself, a string array of detectable objects, which correspond to the tags of the kinds of objects we'd like our agent to know about, and then lastly, the starting and ending offsets of the array.
Okay, cool. So a quick look through the source, and remember you can grab the source from the GitHub repo as well. A couple of questions. One question that Nelson Rush asks is why the arbitrary reward of 5? Why was the number 5 chosen, and what is the significance? 5 is actually a secret number with magical properties. Not really. And as Hunter replies in the chat here on Unity Connect, one thing I'll mention, I noticed there's some people who are watching just on YouTube, right, where there is no chat. Join us on Unity Connect, where we are all chatting and asking and answering questions. If you go to connect.unity.com/events, you will see the listing for the event. You can still join us. I can see like the numbers for YouTube are higher than the numbers over here. So come join us if you're watching silently over there. Speaking of reward values, Hunter answers, choosing the reward values to use can be a fiddly thing. The main thing we want is a clear reward signal. Typically, we try to keep the value between 1 and -1, but sometimes we'll go outside this range if it appears to help the agent learn. This is the kind of stuff where I just find it super fascinating that like, it's like we're helping the agent learn. The agent is like, maybe these values, this agent likes these values better. It's all getting kind of fuzzy and interesting. Is it so hard to give a link? I don't know. Is it? That's a good question. Yeah, so somebody who is mentioning that they thought this was supposed to be tomorrow. There was an issue with the site where, I'm not going to get into all of it, but the date was messed up, so I apologize. But these will be listed on YouTube as well, and you made it here in time, and we will be hanging out for some Q&A. And Arthur says a reward range between 1 and 5 should work for this problem. So give those a try. Yes, as Dan suggests, linking to the Connect chat in the YouTube description. Usually I do that, so thank you. That's a good reminder, actually. Let me go do that right now. I'll put that in there. Oh, I got 2 keyboards. I'm getting confused. Okay, let's move to the next video while I sort myself out here. We are up to, this should be video number 8. Here we go.
With the scene set up the way we'd like, and all of our code in place to handle observations, actions, and rewards, it's time to actually start training this agent. Now, first things first, we want to go back to our brain and ensure that we've set the brain type to external. By setting the brain type to external, we're allowing Python know that we want to be able to control this brain and train its behavior. Once the brain we want is set to external, we can then go to Build Settings and open up the Build Settings window. From here, we just have to ensure that the scene we're interested in, the push block scene, is added, and we can go to Build. Now here, I'm going to save the push block environment into an EMS subdirectory that I've created within the Python subdirectory of the GitHub repo. From there, we just press Save, and this will build the Unity project like it would any other Unity project. With our Unity scene set up, it's time to move to the second step of the workflow, actually training the brains. Once we've actually built our Unity scene as an executable file, we're ready to start training. To start training, what we need to do is go into the Python subdirectory of the GitHub repo that we cloned. We can see that in the environment subfolder, we have the push block environment that we saved. Now, within that Python subdirectory, there are lots of files. 2 of the most important are learn.py, which is the access point to all of the RL and imitation learning algorithms that we've implemented. There's also trainerconfig.yaml, which is what contains all of the hyperparameters used to training all of the example environments that we include with ML-Agents. Now on the right here, I have the trainerconfig file pulled up. You can see that it contains a number of these little sections, and each section starts off with the name of a brain. And so we can see here that we have the push block brain, which corresponds to the brain in our Unity scene, and we have a number of hyperparameters set. Now, in machine learning, it's often the case that hyperparameters need to be finely tuned to get optimal performance. We've included a whole bunch of default parameters for people to just pick up and use. But if you want to adjust these parameters yourself, we have a special subsection of our Unity documentation page that describes the best practices for tuning these models. So once we have our hyperparameters set and our environment built, we can begin the training process. So the way we do that is we start by typing Python 3, then learn.py, which says that we want to launch the learn.py script. From there, we provide the directory and the location of the actual executable that we want to launch and train with. In our case, it's environments push block. From there, we use the --train command to let the learn.py script know that we'd like to actually do training. And then we also can use --run ID to provide a unique identifier to the training process so that we can go back later and load a model or look at training statistics. In our case, I'm just going to call it push A. Once we've pressed this button, the training process will begin. We'll notice that a window pops up here, which is our actual training window, and also a number of things were printed on the terminal window. We have our training parameters. We also have the information from the Unity environment itself. So we have the academy that was called academy, we have the brain that was called push block brain, and we have all the specifics about the parameters such that the vector observation space size was 70. We also then print out those hyperparameters that we put into the trainer config, and looking here is a great way to ensure that all the hyperparameters are set to what you'd like them to be. Now once this is launched, we can see that the training process has begun. If we wait a moment, we'll notice that information about how well training is doing will start to print on the screen. We can see it right here at the very bottom. The push block brain has currently been 2,000 steps into the training process and is right now not doing so well with an average reward of -1.
Okay, nice. So some interesting questions in the chat. Per Fernandez is asking, will ML be supported for the other consoles, such as Switch and PlayStation 4 or PlayStation 5? Whoa, I didn't even know about PlayStation 5. Do you have some secret info? No NDA violations here. I actually don't know if there is a PlayStation 5 or not, so I'm not revealing anything. Or we will need to create our own framework for those environments. And as Vladimir answers, ML will definitely be supported on other platforms. I can't speak for dates as of yet, but this is definitely a work in progress. So looking to expand the number of supported platforms, but no hard commitments as of yet. Keep in mind, right, this is the 0.3 release, so we're still early stages. And then some interesting questions about like intermittent rewards, right? I think this was Nelson Rush is thinking about kind of intermittent rewards, random rewards, the way that works on human players, that when a reward is kind of a little bit unpredictable, people get kind of obsessed with it. I don't think that would work with this algorithm because there are a lot of emotions missing. And I think you would probably just add noise by adding randomness. Yeah, as Hunter says, if you want a clear reward for a behavior that you want to encourage, that reward shouldn't change or it would confuse the agent, right? And this is kind of important, right? The idea of intermittent rewards, right, is usually more like stuff like loot boxes than it is actually teaching someone something, right? If you are, teaching an animal a behavior, you do not want to intermittently switch it up and punish them for doing the right thing, because it's gonna screw them up. So don't do that. Don't do that to your little robots either. All right, let's see. Let's see what other folks are saying. Yep, for folks asking to if they can contribute to the project, Vladimir says you're welcome to join the ML-Agents developer community on GitHub. Please do. Okay, let's see. Okay, good. All right. So let us move right along and continue.
All right, so let's take a look at the agents as they're training. As you can see right now, they're kind of dumb. They just kind of go forward, back, left, right, indiscreetly. But after a while, once that orange block touches the goal, they realize that in order to get a reward, they need to push the orange block towards the goal. Over time, we should see that they'll get smarter and smarter. So let's just check on them again here in just a minute. Okay, so it's been about a minute. Let's check on the agents. We can see that there's a lot more green, which means that they're scoring a lot more goals. The total training time so far has been less than 2 minutes. So you can see how, in a simple environment, the agent can learn pretty quickly what it needs to do.
Now, once we've gotten performance that we like, and in our case, since 5.0 is the highest possible reward, and we're already at 4.96, I'm pretty happy with it, we can now press Ctrl+C to early terminate the training process. And what this is going to do is save our model and export the all-important bytes file for us to use. Once our brain is trained in a way that we like, we can now take that trained brain and import it back into our Unity project. Once the training process is fully terminated, we can go find the bytes file. If we look in the Python subdirectory of our GitHub repo that we cloned, we can look under Models and then find the name of the run ID that we put in. In our case, that's push1. Within the subfolder of that run ID, there'll be a .bytes file. This file corresponds to the frozen neural net graph that we can then import back into Unity. And importing is as easy as simply dragging and dropping into the assets folder. Once our model has been dragged and dropped, we can simply switch to an internal brain and drag the model from the assets window into the graph model placeholder. From here, we simply press play, and we can watch our agent behave just as we've trained it to.
I love watching those dumb little robots try to do things. It's amazing. And I still find it sort of amazing and scary that they can actually learn to do it right so quickly. It's wild. So Chris is asking, after successfully training an agent, how complicated is it to integrate the quote-unquote black box AI into a commercial game? I mean, I think depends what your commercial game is, right? But that's basically the process that we're seeing here, right? Where we train the agent sort of offline, right? Or we train the agent during production, and then that outputs this trained neural network brain asset that we can then embed back into a Unity project and then deploy. Now, actually, this is a question from me to Hunter and Arthur. What is the performance impact of running one of these already trained brains, right? I know we're not at a point where we can train a brain during gameplay, right, or have it learn from the players, but once we've kind of rendered out, for lack of a better term, or once we've trained a model, trained the brain, and we embed it in our game, what is the performance cost of running one of these models at runtime, let's say on a PC or even on like a mobile device? I am curious to hear that. Okay, let's watch the last video, and then we'll continue.
So we just walked you through the process of taking a Unity scene that's set up as a game, adding in ML agents, including all the pieces needed to actually train your intelligent agents, taking that Unity scene and training it as a learning environment, getting the behavior we want, and then taking the resulting neural net model, putting it back into our Unity project in a way that we can take and ship in a real game.
So if you want to get started using ML agents yourself, go grab it on GitHub. It's Unity Technologies/ML Agents. If you have any feedback for us, or if you have any questions about how to incorporate ML agents into an existing project, feel free to send us an email, hit us up on Twitter. Just let us know what you need help with, and we'll help as best as we can. Thanks a lot.
Thanks for listening.
Okay, cool. So super cool, super interesting stuff. A nice little introductory session on how to get yourself up and running using the ML agents released content from us at Unity. So if you haven't grabbed it, please do grab the, oh, actually let me put